So cool, we're recording. Okay. So as I was saying, I think like, well, I'm just gonna warn you all first of all, I have some laundry in the laundry room. So like in maybe like 30 minutes, I'm just gonna run down, put that in the dryer. We'll have like a 5 minute break or whatever, but then we can keep going. Okay. So the first thing we wanted to do though, right, was like make our equation sheet. So I guess let's just like knock that out real quick. And I actually I have the exams or the problems here actually, and so like I can just look at these and make sure that we don't miss anything important. Um, but let's just start, I guess, with like friction, right? Because that was like the sort of oldest topic, right? We'll try to go in order here, I guess. So friction, right? Um, we have two kinds, static and kinetic. Right, so let's talk about both of these. Remember that static friction is defined with an inequality, right? And so it just looks like the force of static friction being less than or equal to a coefficient times the normal force on an object, right? So there's that. We'll talk more about this in a couple seconds here, but let's also just put down that kinetic friction, right, is going to be given by the kinetic coefficient times the normal force. So can everybody see this okay? Should I zoom in or are we good? It's so strange. Yeah, I can zoom in, cool, because like I feel like I say something and then people hear me like 10 seconds later, which is I'm sure exactly what's happening, but it's still very weird. Um, okay, cool. So is this better? Cool. Okay, good stuff. So that's that, right? And I think that what I want to stress is that the kinetic friction is just constant, right? In as much as the normal force is constant on an object. However, the uh, static friction, right, is variable, I guess we could say. And so, like, what you might want to think about here is like maybe an object like on a surface with a non-zero coefficient of static friction, right, that you're trying to push like a box, right, would be like sort of what we typically think about maybe. Um, and let me just say this, like, uh, it can match the applied force on an object up to a maximum of, and we'll just say something like x of s max, and then this will be given by an equality, right? And so this is something that's gonna, you know, it's important to remember, right? Is that it's variable, and it sort of like can attain a range of values depending on like what the applied force is, and we're thinking of an applied force that's like in the horizontal direction, right? That's parallel to say the ground if we're imagining like a box resting on the floor. Okay, so is everybody good with that? Like, do I need to talk more about how this is a variable force, or is that okay? Okay, cool. And if you, yeah, if you have questions, we can always come back to it, so that's totally fine. Okay, let's talk, since we're talking about forces, then let's talk about Hooke's law, right? Because we're going to need this as well. Now, Hooke's law is just, like, we could write it for one-dimensional situations like this, maybe. We could just write that the force, actually, I want to write it like this, spring force. And it's just given by negative kx. Yeah, so for the person asking the values change based off how much force is applied basically, then yeah, that's a good way to sort of summarize it. Now you do have to be sort of careful because like there's a few different ways the friction force in general could change, right? Like if you're say pushing down on something that's resting on the floor, then you're increasing the normal force on it, right? So you could have an increase in say like the maximum static friction force because of that sort of action, right? Or you could just think of like the kinetic friction force not caring if you push on something horizontally, but the static friction force, right, will actually, let me say this. So like if you have a horizontal force being applied to an object, and there is a non-zero coefficient of static friction, the best thing to do is probably just start by comparing the magnitude of the applied force to the magnitude of the maximum static friction force, right? This is what I would suggest you do for every problem you encounter that involves static friction, right? Because the first question you want to ask yourself is probably something like, can the applied force overcome the maximum static friction force? And that is, I think, what I want to say here. Now, okay, Hooke's law. So this can be tricky, especially the negative sign, right? Somebody's asking about that. And all the negative sign means in Hooke's law is that the spring wants to get back to its equilibrium position, right? Let me just make like a crappy sketch here if I can. So let's say, right, that we have a spring. Let me see here. That looks like this, that's, you know, at its equilibrium length, right? Maybe it's like attached to the wall or something. So this is the wall here, right? If we say that the equilibrium position is here, and we call this x equals 0, right, which is sort of a very natural thing to do, then if you put or you pull the spring, right, let's imagine maybe there's an object attached to it too, right? If you pull it now so that like it's over here, remember the spring wants to get back to its equilibrium position, and the x value over here is positive, so the force should point to the left, right? And that's where this negative sign is important because it tells you the direction. Alternatively, if you push on the spring, now you're compressing it, right? Let's say you put it over here now, like at this x position. These are all supposed to be like along the same horizontal line, but I think you get the idea. You push on the spring like this now, right? And you have a negative x value here, right? Because let me just put this in. X over here is greater than 0. Writing with the mouse is really hard. X is less than 0. Right? And so now we're over here where x is negative. And then again, if you look like negative k times this x value, which is negative, gives you a positive numerical value for this force, which means it points to the right. And that's why we write it with the negative sign. Alternatively, you could write it without the negative sign and just use sort of your intuition to get the direction. Either way is fine, I guess, but don't like double count the negative sign, I guess, is the important thing, right? Or just make sure that like you're being mindful of whether your x value is positive or negative for like a given configuration. And yeah, k is the spring constant, and it is positive, right? That's the thing that is important to remember. And x can be positive or negative. So basically, the reason there's a negative sign in here is because we're allowing for x to be positive or negative. But as I said, like if you can just remember that the force that the spring exerts will always want to point toward the equilibrium position, then you're good. Our x value is negative when we use the negative in the equation. We don't use both. No, you would, right? You would use the negative in the equation because remember that gives you a positive force, right? So when you plug the numbers in, you get a force that's positive, which means it points to the right. Yeah. So how much credit will we lose if we add the correct sign on the answer, but we forget somewhere in the equation? I mean, let's see here. I don't know. I mean, just try to get it right, you know? Like, don't be so negative, okay? But if and when that happens, we can talk about it. So if x is negative, then the force is positive, yes, right? And if x is positive, then the force is negative, and that's maybe the one way to think about it. Cool. But you also, like I said, just remember that the force should point to the equilibrium position of the spring, right? And make a sketch, and it'll be helpful, I think, if you just basically say, I want my x equals 0 position to be at the equilibrium point of the end of the spring, and you'd be good to go. Let's see here. Is this good, or do I need to talk about this more? People are asking good questions, but I think I answered them all. Is this okay? Okay, cool. All right, so then let's move on to energy and like the work energy theorem, right? So first of all, I think like we just want to define work in general, right? And we could say that work in general is just going to be given by this. We could say it's a dot product, right? It's F dot D, where, remember, these should be forces. So F dot D, or we could always write FD cosine theta. Right, now remember that theta is the angle between the force vector and the displacement vector. And usually it will be either 0 degrees or 180 degrees, right? And cosine is bounded between -1 and 1. So what this means is that your work should be something like, yeah, so when I bold the letters, that means it's a vector. I'm not going to put arrows over them when I'm typing them because I'm not insane. But what this means, right, is that your work, right, like a given value that you calculate for work should be between negative FD and positive FD, right? So you have like a little sanity check here you can do for a calculation that involves numbers, which is this, right? So do I need to talk more about this, or do we feel okay about work? While people are like coming up with answers for that, I do want to stress, right, that it's a scalar. So it doesn't make sense to say like the x component of work or the y component of work, right? It's a scalar. And one of the things we're going to be looking for is definitely making sure that work is a scalar. And so just keep that in mind. So for people who are wondering about the inequality, this just comes down to the fact that this is not super important, right? But I'll talk about it just really quickly here. That cosine of theta, right, is bounded between the values of -1 and 1, right? Meaning it can never be larger than +1, and it can never be smaller than -1. And so what that means is that for a given force and a given displacement, right, constant force and say a linear, I guess displacements are always linear, but you should never get something that is less than -FD or larger than +FD, just because it's just a math thing, right? Because you just plot this, right? You graph it on your calculator, you see that it never grows larger than +1, never grows smaller than -1. But that's not super important. Just like something I wanted to point out. Does that make sense though for people who are asking about the inequality? Yeah, I'm loving the emotes. So, let's see here. Probably the next thing to just talk about would be like the work energy theorem, right? Now, we could write this as the net work done on an object is equal to its change in kinetic energy, right? So if we like expand this out, say we have multiple forces acting on an object, the left-hand side of this is going to look like the work done by the first force plus the work done by the second force plus like all the way down to the work done by the nth force, right? If there are n forces. And the kinetic energy, the change in kinetic energy is just probably what we would expect, right? It's 1/2 mv final squared minus 1/2 mv initial squared. Yeah. And so it's important, right, that you remember that the work here, the network that's being that we're thinking about is just all the works, right? Whether they are there because of conservative or non-conservative forces. So you want to just make sure you're good with that. Yeah. So work energy, I think, and I've stressed this in like every recitation so far that we've had, right? So I hope everybody's good with this. And I mean, like, we can definitely talk more about this when we look at some examples too, if people need me to talk about this more. So then let's, what do we want to do? Probably just like define, yeah, so you could think of the network as being the work done by the net force over like the displacement of the object, right? But more often than not, we are just because of the way like we're given problems to solve, we have to break it down into the different works being done by the different forces, right? But that's fine. That's a fine way to think about it. So then let's, what did I want to talk about next? I guess the different forms of energy, right? So different forms of energy. So we already said basically that K, wait, I think somebody actually said something here. Work is a scalar, but it can be positive or negative. Yeah, it can be positive or negative. Just like energy can be positive or negative, right? Even though energy is also a scalar. So as far as like the different forms of energy we have kinetic energy, right? It's just 1/2 mv squared. I probably don't need to say this, but just in case, like this is always going to be greater than or equal to 0, right? Because you have a mass that should be positive. You're squaring v, right? So like regardless of what v is, it should be positive, and so your kinetic energy should always be greater than or equal to 0, right? I understand why work can be negative, but why energy? Yeah. Well, okay, because work and energy are the same thing in essence, right? I mean, because we have an equation here where for instance, where we write that like the work done on something equals its kinetic energy. I would say, like, don't worry so much about the fact that energy can be negative. Maybe just accept it because we know that work is energy, and work can be negative. Is that okay? We don't really need to like talk about, I think, the philosophy of this, right? And it's largely a math thing. It's largely a math thing. Negative energy is energy being taken away. Well, energy is like a state, right? It's like you look at some object at some point in time, and you know, by making certain assumptions, right? Like for instance, defining where your y = 0 position is, if we're talking about gravitational potential energy, then like it kind of doesn't make sense to say that negative energy is energy being taken away, because energy is like a state. You could say it's a state variable, right? It describes something at a given instant. Um, so maybe what you meant to say is negative work means energy is being taken away, and I think that's fine. That's fine to say. But negative energy is just kind of, it's kind of whatever. I mean, okay, so these are good questions. So I just want to make sure that like I'm not really going into elaborate details about stuff that's not important or that you won't need, right? So let's talk about elastic potential energy, right? So I'll call this U sub S. Yeah, I can mod you. Like, why not? I guess you're not gonna just like start banning people or anything, right? Yeah, I'll mod you. I'll mod you during the break. Okay, so because I have to figure out how to do that, unless there's like an easy command that I can just copy and paste that you can put in chat. So elastic potential energy, right, is going to be 1/2 K x squared. Now, just another thing, right, as a sanity check is like this should always be greater than or equal to 0 as well, because as we were just talking about, your spring constant is positive, and x can be negative or positive, right? But we are squaring it, so it doesn't matter. When we square it, it just becomes positive. So this is probably not something I really need to say, but just in case, right? If you find yourself writing down that the elastic potential energy is negative, you should double check your work. And then we'll talk about the gravitational potential energy. Now, this is going to be mgy, right? Where y is the vertical position of your object. Now, this can be maybe I won't even like put the inequality here or whatever. I'm just going to say that it can be negative, 0, or positive, right? Because the first thing you want to do when you're, let me put this in words actually. So the first thing to do is say determine where the equilibrium position of the spring is, right? We can't choose where this is. If the spring is like fixed to something, right? This is sort of uniquely determined or defined. Then also determine, let's just say, the equilibrium position for gravitational potential energy. And what this means, right, is that we can define y equals 0 to be wherever we want. I don't know that I'll be emailing this document out, especially because it's going to be, I don't know, it's going to be, yeah, I guess I can email it out. Why not? Yeah. But I mean, we're going to go like, you know, probably like 2 or 3 pages of just equations, I guess. And that's, I don't know. I don't know actually why that's important. The first thing to do is determine where the equilibrium position of the spring is. So we can't, let me say, we can't decide where this is. And also determine the equilibrium position for gravitational potential energy. Is everybody good, before I answer the question about the equilibrium position of the spring, is everybody good with this idea that we can put y equals 0 to be wherever we want for purposes of calculating gravitational potential energy? Is this okay? Because I mean, the important thing is that you decide where your y equals 0 is, and then you just respect that decision, right? You just make sure that all the work that you do is consistent with that, and you should be fine. Okay, cool. So just make sure that you do it, right? Because I have seen lots of students who are like, yeah, let's solve this problem, and then like, you know, they start writing equations and stuff, but they don't do that. I mean, I do it sometimes too, right? So it's easy to do, but just try to remember. Okay, so that's cool. These are the different forms of energy. Now we can talk about conservation of energy. So let's see, the exam that I wrote, right, is what you're talking about, because I think Dr. Nero's exam has like the answers in the back. I'll start putting this down though. Yeah, I can. So like some people have emailed me about it. What I did was I just went into Canvas and looked for a student who got 100 on it and copied their answers down. But so I can't. I'm not going to send out a solution just because I don't have one handy. But I can at least give you the answers. Also in the email that I send out with the document then. Okay, cool. So conservation of energy, right? What we want to say is that is essentially that the change in mechanical energy of a system or an object or whatever is given by the work done by the non-conservative forces on it, right? And we can just write out that like generally the mechanical energy, right, is going to look like this. It's going to look like 1/2 mv squared plus mgy plus 1/2 k x squared, right? Or maybe more generally, it's just k plus the gravitational potential energy plus the elastic potential energy, right? And so then when you notice that there's a change in mechanical energy, you want to look, right? Like, so what I'm saying is that like if some object initially has some mechanical energy at some point, right? And then some later point in its motion, it has a value of mechanical energy that's numerically different. Like we know that there's a non-conservative force or multiple non-conservative forces doing work on it, right? And so just remember that for our purposes, the only two conservative forces are the gravitational force and the spring force. So would we ever have to use conservation of energy, or could we always use work energy theorem instead, right? They're the same thing. That's the simplest answer is that they will give you the same answer to any given problem, right? And so it's just kind of a matter of I guess your preference, or say if you're told specifically to use the work energy theorem, right? But like if like the problem is stated such that you can do it either way, it doesn't really matter. I would just choose whichever you're more comfortable with. Personally, I like conservation of energy because I think that it's easier just to worry about the work done by the non-conservative forces. And so, but it doesn't matter, right? And like one of the examples that I did for recitation, we did one problem and we did it both ways and we got the same result. So, and that's not just a quirk of that problem. That's like something that will always happen if you're doing it right, right? So let's see here. So somebody says this equation sometimes turns out negative. Does it make a difference, or how do we know what is right? Well, yeah. So like, I want to say that almost always, right, you should have that, for instance, like the work done by friction or the work done by the drag force is negative, because these are dissipative forces, right? And we could think of them as taking energy out of our system, if you want to think of it that way. But like, think about what friction and drag do, right? For instance, like object moving in one dimension, subject to a friction force or a drag force, or possibly both, like it's going to slow down. And so it's losing kinetic energy, right? And so you should expect that the work done by friction or the work done by the drag force in any given situation will be negative. And if you find the opposite, right? If you find that they are positive according to your calculations, like at best, you should double check them, right? I'm trying to think of an instance in which like friction or drag do positive work, and I'm not coming up with anything. So I would say they should just basically always be negative. So for the work energy theorem, if there's potential energy present in the system, do you then include potential energy, or do you only ever include a change in KE? So, I mean, what this looks like, right, is this just looks like what's up with all the resident sleepers, by the way? Are people tired? What this looks like, right, is just like delta K plus delta U plus delta U sub S, right? Equals the work done by the non-conservative forces. And so what ends up happening, right, when you apply the work energy theorem is that you have to account for like the work done by the gravitational force. Copy pasta, we love that. You have to account for the work done by the gravitational force, right? And so you wouldn't account like for the gravitational potential energy of an object if you're using the work energy theorem, because then you're basically double counting gravity, right? And so don't do that. And yes, I agree, Hatridge is very thick. But you want to like just choose this or this, right? You don't want to like hybridize them. You don't want to sort of like use one for half the problem and the other for like the other half of the problem. Just keep them separate, right? Because that's how people make mistakes. I've seen lots of people make mistakes that way. So are we good with the conservative forces and non-conservative forces? Like I think I was just saying, for instance, you know, drag is going to be non-conservative, friction is going to be non-conservative, any force that you could apply or I could apply, right, is going to be non-conservative, tension, non-conservative, and so forth, right? Because it just comes down to the fact that the only two conservative forces that we encounter in this class are the gravitational force and the spring force, okay? Are we good with this? Do I need to talk? Oh, 69 viewers, nice. Do I need to talk more about this, or can we move on? Okay, move on. All right, cool. So tomorrow, right, nobody's going to mix conservation of energy and the work energy theorem up, right? You're going to just choose one and stick with it, okay? That's my timer. So let me just think about. Okay, so what I want to do is I want to just talk about momentum, because I guess that's the last big thing, and we can talk about, I guess, a uniform circular motion. Then I'm going to pause for a little bit, go put my laundry in the dryer, and then we can like look at some example problems maybe. So momentum in collisions, I guess, would be important. Now, like linear momentum, right, is just defined to be the mass of an object times its velocity. Now, this is a vector, right? So we want to, you know, realize that energy is a scalar and momentum is a vector. And so one way we could write this, for instance, is like we could just write this as the mass out in front of a velocity vector. If we're talking about 3 dimensions, right, you know, your vector would have 3 components, but we won't really do anything with 3 dimensions. But this is what momentum is, okay? Now I would say that as far as collisions go, conservation of momentum will apply more often than conservation of energy. And, you know, what do I mean by conservation of momentum, right? I mean just saying that the initial momentum, I don't want to capitalize that, the initial momentum equals the final momentum, right? It's a vector. And so, okay, let me ask you then, just so we're clear on this, right? Let's say we have like two objects and there's two-dimensional motion. How many equations is, well, actually, let me start by saying this. How many terms will I have over here for this left momentum term, right? So I'm saying two objects moving in two dimensions, right? I want to figure out what the total momentum of that system is. So I'll have, yeah, I guess the question isn't 100% clear, but what I want to stress is that when we apply conservation of momentum, it's like the momentum of the system, right? It's not just like one object. So if we have two objects moving in two dimensions, then we would have separate equations with two terms for each direction, right? So let me write something down here. So like what this would give, oh, why does it do the bold? Is something like this, right? Let me be fancy here. Just because this is like another mistake that I see people making. So this says something like the momentum, the initial momentum of, I don't know, object A in the x direction, right? Plus the initial momentum of object B in the x direction equals, and then I'll just change this to get rid of the zeros, right? So it equals the final momentum of object A in the x direction plus the final momentum of object B in the x direction, right? And so then the same equation here will work for y. I just changed the x's to y's, right? So make sure that you're just like accounting for the momentum of each object. Now, it can definitely be zero, right? If an object is just at rest, it has zero momentum by definition. But it's a good idea to write out every term. And so this is what this would look like for, say, two objects that can move in two dimensions. So we should probably like categorize the different kinds of collisions, right? This would probably be a good idea. And like I think everybody knows by now, I can't remember what they're called, but I mean I know how to do this stuff, right? So so what Wikipedia is telling me here is that an inelastic collision means that kinetic energy is lost, right? So let's do this. So for inelastic collisions, we could say that delta K is, let's say this. Let's say that K initial is not equal to K final, right? Can somebody just double check me? Because like I said, I can never remember the damn terms, but I think that inelastic means that we can't apply conservation of energy. And then for elastic collisions, we could write that, okay, cool, thank you. We could write that the initial momentum equals the final momentum, and the initial kinetic energy equals the final kinetic energy. And now the sort of the paradigm for an elastic collision, right, is like two objects that collide and stick together. So for sure, right? Like if you see a problem where the objects collide and stick together, like wait. No, sorry, this would be an inelastic collision, my bad. I confused myself there. Yeah, so if you see like a collision where two objects collide and stick together, you know that you can't apply conservation of energy, but you can apply conservation of momentum, right? And that's like what I'm saying is that conservation of momentum will work for you more often for problems involving collisions than conservation of energy. So these are just like the two different types, right? And you could talk about like perfectly inelastic, which is, I guess, that this is what that is, right? Perfectly inelastic, or completely inelastic, right? But yeah, and so here's the point, right? Like, who gives a damn about the words, right? Because we know that if two objects collide and stick together, we can't apply conservation of energy, okay? And so that is very important to remember, okay? But notice that for both of these cases, right, conservation of momentum works, but conservation of energy doesn't for both, okay? So just be good with that, right? So then how do we feel about like solving these systems of equations that arise when we have, say, an elastic collision and we need to like account for two objects that are doing stuff? Like, do we feel okay about that? Yeah, conservation of energy is the same as conservation of mechanical energy. So we could have just as well written that like E initial equals E final here, right? So that's a good question. But like, do we feel good about the math when it comes to solving these problems? Like, say, for an elastic collision where both momentum and kinetic energy are conserved. Okay, so I can talk about like what you would do here. I think you've probably been given the formulas, right? But just in case like you want to see how you would solve this, maybe in like one dimension we could do it. So like if we have two objects colliding in one dimension. So how do we differentiate between elastic and inelastic if it's not? I wouldn't really worry so much about that. So like usually instructors will tell you, first of all, if it's like an elastic or inelastic collision, or they'll tell you like, hey, the objects collide and stick together, right? And so if they say like either of those two things, then you can, almost immediately classify the collision, right? So I wouldn't really worry so much about like trying to figure out if it's inelastic or elastic, because I guess that would be hard if you're not told in so many words. Okay, so what we would do, right, is like, let's just say we would have that the initial, and I'll show you a little trick here actually. The initial momentum equals the final momentum. Let's just talk about the x direction to be general, right? Or actually not general, to be specific. So then, and we also have that the initial, and we'll just say that the initial kinetic energy equals the final kinetic energy, right? So we could do this. We could say, well, one object has mass 1. Let's say it's moving at speed u, right? I'm not going to write more than one subscript, so I'll just use one of I'll call one of their velocities u and the other one v, okay? And we have mass 2, it's moving at, say, v naught, right? So this is my initial momentum in the x direction, because u and v will only have x components. And then we just set this equal to the final, right? Final momentum, u, m1u plus m2v, okay? And correspondingly, right, the kinetic energies look like this: 1/2 m1 u naught squared plus 1/2 m2 v naught squared equals 1/2 m1 u squared plus 1/2 m2 v squared. Okay, so here's what I would do, right? to like clean this up a little bit. Well, the first thing you can do here is you can just multiply everything by 2, right, to get rid of the 1/2. That's something. But you could also do this, right? You could like, so you could define the ratio of the masses to be, and let's say something like this. I'll use a fancy M. So let's see, hang on. In reality, there's no such thing as a collision where energy is conserved. Well, energy is always conserved, actually. It's like one of the most sort of cherished principles of physics. It's just like, can we, you know, keep track of where the energy goes, right, is the question, the practical question. And so these won't be true for inelastic collisions, right, because we can't apply conservation of energy or conservation of kinetic energy, say. Well, and yeah, so okay, so u is just a velocity, right? I don't want to write like v1 and v2 0. You know, I just want to try to keep it simple. So u, vw, those can all be velocities or speeds, okay? And the person asking, do we need both of those equations, or can we solve only using the top one? Well, that depends on how many unknowns you have, right? Because if you have 2, okay, let's do this. Let me make this clear because I could see this being confusing. So this is an unknown. I'm putting it in red, right? This is also an unknown. So what we're doing is we're assuming that we kind of know everything except for what's in red here, right? So then correspondingly, this is unknown. And this is also unknown, right? Is that better? So I'm saying that we know everything except for u and v, because that's typically how these problems go, right? You want to figure out what's going on after the collision if you know what was going on before the collision. So I'm gonna keep going with this, and you can tell me if that's clear or not. But what I'm gonna say is, like, we could do this little algebraic trick where we just say, well, I kind of want to try to get rid of the masses, but like they're different. So how do I do that? And the answer is, like, we just think about the ratio of the masses. Oh, why is it using this awful? Okay, let me fix this because this is gonna bug me. Can I like highlight this? There we go. Thank you. Yes, elastic collisions get me going too. That's not the right one. Just bear with me here. Is it? It's this one. Okay, why can't I? All right, let's see what happens here. Okay, so I'm going to define this to be the ratio of 2 masses. I'm going to say, let's just introduce this dimensionless constant. We'll call it script m. Like, you could write u, or you could write mu or something like that if you don't want to try to write like a fancy m. But the point is that it's just the first mass divided by the second mass, right? So you might be like, well, why the hell would I do this? And what this allows us to do is almost effectively cancel the masses, right? Because I could then write this equation and divide everything by m1, right? Like this. Both sides, just divide each term by m1. And then what I find, right, well, this, of course, is just 1. This is going to be this fancy m that I wrote. This is also 1, so we just get rid of it. And this is going to be also the, wait, I did that wrong. Okay, let me just fix this really quickly. This should be m2 over m1. But it doesn't matter, right? Because like you would just have 1 over m, script m anyway. Okay. So then this would be script m also. And we know this, so it should be in black. Okay, so this looks a little bit nicer, right, than the original equation. Like, we're able to get rid of some of the coefficients in front of some things, right? And you could just do the exact same thing for this equation. I'll just do it, I guess, because I already did it for the first equation. So first thing we do, right, to clean this up is we get rid of the 1/2. Okay, that's nice. And then we could go through, and as I said, we just divide each term by m1, right? So this coefficient just goes away. m2 over m1, that's just the script m, right? m1 over m1, 1. m2 over m1, script m. So now we have this. This is our system of equations, right? And I think we all agree that this looks a little bit nicer, right? I mean, it's still not great, but we've cleaned it up a good amount, I think. Somebody's asking, we can only use the two equations we have in elastic collision. Yeah, so we're talking about an elastic collision here. Maybe I should just put that in words. Colliding elastically in one dimension. Okay, cool. So then now it's like all you do here, right, is you just solve the top equation, right? The conservation of momentum equation. Solve it for u or solve it for v, and then plug that into the bottom equation. Now the algebra is going to get a little bit gross, right? Because you're going to be squaring something, you have to expand that out, but like at least you don't have to write fractions or anything like that, right? So the blueprint here is like solve the momentum equation for u or v, then plug that in to the energy equation. And it's just math, right? You just do the algebra. I mean, sometimes, you know, it's just gross, but you have to do it. Is this clear? Is like what I'm trying to describe here? I mean, I know it might not be very clear, but like, is this okay? Do people see that how like I would just suggest trying to simplify the algebra as much as possible? Now, and remember that this, right, this is just a number because we are dividing a mass by a mass. And so it's just a number. Now, if you had, say, like one mass that was 10 kilograms and the other was 5, it would actually be like an integer. It would be a nice number, right? And so that's cool, I think. And yeah, you don't have to do this, right? I'm just trying to show you a way of making it easier. And by the way, No Flux Given, I think, is like one of my good friends' Instagram username. It's not you, Lucas, is it? Okay, so anyway, this is what we do here, and then we just math it up, okay? Are we good? Because I think that the only other thing to talk about really quickly is circular motion. Okay. I'll like obviously keep checking for questions, but the last thing will be let's say uniform circular motion. And the idea here is that we just write Newton's second law as we would, right, for something that is not moving in a circle, but we have to now concern ourselves with the centripetal direction, which means the direction pointing towards the center of the circle. And we sum our forces, right, that have components in the centripetal direction, and we set them equal to mv squared over r, right, where r is the radius of the circle. Would you be able to do a system of equations with u1 plus v1 equals u2 plus v2? If you had two unknowns, you could solve it for one and plug back into the original momentum equation. Well, the thing is that, like, just from a math perspective, right, just totally divorced from the physics, we need at least as many equations as unknowns, right? Jesus Christ, okay. We need at least as many equations as unknowns. And so make sure that, like, before you try to solve anything, right, that's what you have, because if you don't, like, you're not going to get anywhere, right? Let's see here. In the momentum equation, what is u? Yeah, it's a velocity. I just don't want to write like primes or more than one subscript. Yeah, it's just a v in essence. Okay. All right, is this good? I think we were talking about circular motion. Okay, so remember, right, that v here, first of all, is the tangential, well, it's the tangential speed, let's say. And so the velocity vector that corresponds to this v is always going to be tangent to the circle through which the object is moving, right? Now, what you should never do is, like, when you actually get down to summing your forces, is write something like this, right? That the centripetal force equals mv squared over r. And do people see what I'm saying here? Because first of all, this, like, isn't meant to be the same thing symbolically as this. But what I will say is that, just because I think that Hatridge, like, harped on this too, and it's good that he did, but that you should always be able to identify one of the forces that we know and love, right? Like tension, the gravitational force, friction, etc., as the centripetal force. Or as let's say, one of the centripetal forces, right? Because you could probably have a situation like for instance the quiz, right? There was like tension and the gravitational force for that one problem, right? With the thing swinging in a circle, like those are both centripetal forces. But we didn't just write FC, right? Or we didn't, like, worse, we didn't write FC plus T plus mg equals mv squared over r because there was no centripetal force. There was no, how do I say this? Because there were only two forces acting on the object, right? There weren't any more. So FC isn't equal to mv. So the net force in the centripetal, Jesus Christ. The net force in the centripetal direction is mv squared over r, right? And this is going to look like something like, you know, Matt Coos, he didn't invite me to his wedding. He's basically dead to me. Sorry, some people from undergrad are here to antagonize me, so just ignore that, I guess. But let's focus, like, on the quiz problem. Does everybody remember, right, like the top of the circle when the mass was being swung around on a string in a circle? Right there, it was like the what we would put here is T plus mg, where we had tension and the gravitational force, right? No, it's fine, dude. Tension and the gravitational force, right, were equal to the mass times, right? Remember, this is just, we could also say that this is the mass times AC equals that. So the net force in the centripetal direction for uniform circular motion is mv squared over r for the person asking, right? What I'm trying to say, though, is just basically what I put in words here, that you should always be able to identify one of the forces that we've been working with up to this point, right? Like whether it's tension or the gravitational force or friction or whatever, as the centripetal force or one of the forces that has a component in the centripetal direction. Okay, are we good with this? Okay, cool. So I think that, like, I'm just gonna look over this really quickly and make sure that we hit everything that we need, right, for the exam. Let's see here. Yep, got that. Cool. Yeah. Last one here. Well, so when I said the centripetal force was equal to T plus mg, that was for that specific quiz problem, right? I was just trying to come up with an example to make it more concrete. And so for, like, that ball or whatever it was that was being swung around in the circle, right? when it was at the top of the circle, the tension force and the gravitational force were pointing straight down, right? But that was incidentally also our centripetal direction. And so that was just me trying to be concrete here as opposed to general. But it doesn't have to be tension or the gravitational force, but it should always be some force that we can identify, that we've been using up to this point. Jesus Christ. Okay. Can anybody else think of anything that we should talk about as far as like equations and stuff go before we move on to just looking at some problems? Anybody got anything? Drag force, I wouldn't worry about that so much because, like, if anything, what you'll have to do is just account for like the work done by the drag force more indirectly. And oh yeah, impulse, that's good. No, you're not gonna fail, all right? Just yeah, okay. So some of these people here who are like, you know, my friends from undergrad, they're all physics majors too. So you know, like for instance, no flux given, he knows his stuff. So whatever he says in chat, just go with it. But oh, I forgot what I was saying. Oh yeah. Thanks, Lucas. Yeah. I just got my haircut. The drag force, right, is not something that like we'll need to work with directly, but you should like be comfortable with the idea of calculating the work done by drag sort of indirectly, right? Which was like what we did with conservation of energy and setting it equal to the work done by the non-conservative forces, right? There was a quiz problem about that, right? Make sure you understand that. That was like the skier going down the slope, and there was friction and drag. Power, I would say no. Power, don't worry so much about power. Yeah, Jesus. Yeah, don't worry about power. Because I think Hatrid's like doesn't even really care that much about it, right? He's probably made that clear in lecture based on what I've heard. Yeah, so like for the equation for work done by drag, it's tricky, right? Because uh the drag force is proportional to, well, let me say the drag force, right, depends on the velocity of the object. And so working directly with the definition that you were given, right, in lecture of the drag force is going to be tricky. So just think back to the quiz, right, where you calculated indirectly. Hopefully that's what you did. Because if you didn't, you were wrong, right? Yeah, this is what I'm trying to say. Yeah, that's great, Lucas. So what No Flux is given is saying in chat is great. That's I really could not have put it better myself. Now, okay, I'm going to put my laundry in the dryer, right? I'm gonna come back and then we'll work on some example problems. If you haven't already, like hit that follow button for me, please. It'll help me out. And I will see you. Yeah, thanks. I need all the luck I can get. And I'll see you in a few minutes. Okay. Behave yourselves. Okay. Who has questions about specific... Heizo's biggest fan. Who has questions about specific problems? Say from like the stuff that I sent out. Yeah, laundry's good. Need to remember to set a timer. Uh, 8 on the last homework. I bench 1,000 newtons. Okay, let me bring the homework up. See if I can remember my password here. So was this was what, homework 7? People want to look at number 8. Oh no, I didn't finish it. Shame on me. Was this the one? No, this was 7. Nate the Skate, right? Oh, this poor guy. This is the one we wanted to look at. I wouldn't worry about graphs. But who was asking about this? Somebody was asking, right? Do we want to do this one? Yeah, let's get some F's in chat for Nate the Skate. But it is this one, right? This is number 8. Okay, yeah, we can also work through the exam that I wrote. Let's just knock this one out, and then yeah, and then we can do that. Okay, cool. So let me just see here. Okay, 70 kilograms. Yeah, this is good. All right. Let me just split this up. Yeah, so to do a calculation of the work done by the drag force, it would be delta E is just equal to the work done by the non-conservative forces. Yeah, Ryan's biggest fan, 420. I miss you too. Appreciate you being here. But yeah, that's how you do this. Okay. Not this, but that kind of problem. All right, so I'm gonna just do the stuff. This is number 8. So let's say the mass of Nate is gonna be little m. Is it 117 kilograms? the mass of the statue, 835. So let's see here. Hurled himself against a stationary statue of Isaac Newton in a perfectly elastic linear collision. As a result, Isaac started moving at 1.09 meters per second and Nate bounced backward. Okay, so what I would, this is like what, let's see how. Let's say like big V is, the speed at which the statue is moving after the collision, right? And that is 1.09 meters per second. Okay, so this is going to be a situation where we can apply conservation of both momentum and energy, right? So what we do is we just write out the, oh yeah, no, that's probably a good idea. Actually, I don't want to do that though, because like OBS is like really finicky, so I'll just like I'll switch this. This will be better. Good catch though, thank you. And then we just want to also, yeah, I know numbers, right? We hate them, but we also want to write out that the initial kinetic energy equals the final kinetic energy. And so we just fill this in, right? Okay, so for the initial momentum, right, before the collision, we just have Nate's momentum, right? Because the statue is stationary, it's not moving. So we could just write mu naught and then plus 0, right? Just to indicate that we realize that the statue is stationary. So then, let's see here. So after the collision, right, Nate bounces backward, and this is kind of where we have to be careful with, well, you don't have to do this, but this is what I would do, right? We have to be careful with like the directions and the fact that momentum is a vector. And so we can account for the vector nature of momentum by just putting plus or minus signs in front of these terms, right? Just like we would do with forces when we're summing forces in, you know, the X or Y direction or whatever. So if Nate bounces backwards, then we can write this. We can write minus mu for his momentum, right? And this just shows that we know that he's moving to the left now if he was initially moving to the right. Then the statue is going to be moving to the right with some velocity v that we actually know to be 1.09 meters per second. Okay, so this is my conservation of momentum equation. And this will be like a situation where we have two equations and two unknowns. Okay. So then let's fill in the kinetic energy. We have that Nate initially has some kinetic energy, like that. The statue, right, is not moving, so it has no kinetic energy initially. However, after the collision, they're both moving, so they both have kinetic energy. So we could write this. And this is going to, as I was just saying, right, be a system of two equations with two unknowns. So our unknowns are u naught, right, and u. And I think that I said this to most everybody by now, but like, you know that like you're definitely going to want to be comfortable working symbolically for tomorrow, right? So I kind of hope that everybody is. But this is what we have: two equations, two unknowns. So probably like the simplest first step here is to just get rid of all the 1/2 in the conservation of energy equation. Yeah, I mean, two equations, two unknowns basically solved. Yes, very true. And so what do we do here? Somebody tell me, right? What would be the next step to do the math that we need to do? Oh, Jesus Christ. You could do that, yeah. You could divide by yeah, substitution, that's fine too. So like what we would do is probably, yeah, isolate a variable, that's good stuff. So I mean, like from this equation, right, we could say that therefore u naught, right, is just going to be big MV minus mu over little m. And then we could just take that down here, right? So then substitution gives, and then we could just like do this. Now this is u naught from our momentum equation, and then this equals m u squared plus big M big V squared. And so we've essentially turned this into one equation with one unknown. And we could do that thing I was talking about earlier, right, where you take the ratio of the masses. That would be fine. Like that would be sort of an intermediate step just to kind of get rid of some of the mass dependence here. You don't have to do that though, right? That's just like I said, something to help you kind of simplify the algebra. But if we had done that, what we would find is something like this, right? We can still just go through and say, let's divide every term by little m. And so if we did that, we would just get rid of the m there. We would get rid of the m there. And then this would go to big M over little m, right? Which we could just note is just a number. It's just 835 divided by 117, like whatever the hell that is. Is it nice? Let me see here. No, it's not nice. Okay, but that's fine. And so then, like, and if you wanted to, you could, like I said before, right? This is what I think some people were indicating, is that you could just write this as like a different variable. And then when you plug in the numbers at the very end to get your numerical answer, you just, yeah, you plug in 7.136 for this script m. Do people want me to solve this, or are we good moving on? Yeah. So because right, remember what we're doing is we're taking the ratio of the masses just to simplify the algebra a little bit. Yeah, well, man, yeah. No, you can't use Mathematica, unfortunately. I wish you could, but no. Okay, so do we still need V1F? I'm not sure what you mean by V1F. But like looking at this, right? Remember, big V is known. All the masses are known. So the only unknown in this equation is U. Right? Okay. You know, California's a long way to go. Okay, I don't have time. Are we good with this? Do people want to see like the algebra done, or should we move on? I would suggest, right, that if you are not feeling comfortable uh with what you would do next, right? Like if you know what to do next, but like you are not sure that you could do it, definitely give it a try at some point before the exam tomorrow. And you know, you can always just plug this into like Wolfram Alpha and make sure that you end up getting the right result, or just check the numbers at the end when you've solved for it. But I would strongly suggest that you try to solve this symbolically up till the last very last step. Do you have to square the ugly fraction? I mean, you would probably want to expand it, right? Because you need to get u on one side of the equation and everything else on the other. Yeah, you take the square root, sure, great. No, you want to expand it, yeah. For elastic collisions, doesn't v1 plus u1 equal v2 plus u2? That would be assuming that the masses are the same, though, right? So that would be okay as long as both the objects have the same mass. Because what you're saying, right? v1 plus u1 equals v2 plus u2 is just conservation of momentum with the masses canceled. No, I don't know, but I think that really the only is it a difference of squares? I don't really know about that. But what I would do is I would just expand this, okay? Everybody good with that? I mean, what I mean is just right that this is this, and then you just expand. Okay, somebody, okay, yo. All right, let's get rid of that. Okay, number 4 from the energy homework. Which one is that? Is that the same homework or is it a different one? Not, this is momentum. 4. Let's see about this. Yeah, this is a good one, I think. Let me just make sure. Okay, let me just wrap up the discussion about the one with the collision though. So you can't assume that he bounces back with the same speed. Or was it this one? Especially because like they ask you to solve for it, right? They say what is the speed after, and so you can't assume it's the same, right? I mean, there's like really like sure you can do some fancy stuff with the math, but the only way around this is just doing this, right? Solving this for you. Just be careful, you know, step by step, right? Don't try to skip steps because that's how you make mistakes. Just go through and take your time. Hopefully, like with 110 minutes, like everybody feels like they more or less have enough time, and it's good to go. Okay, cool. Okay, so what do people want to do? We could look at the practices. Yeah, let's do that. Hey, okay, can somebody, like, can one of my students DM me real quick? Like, DM me your name and I'll make you a mod and you can start banning people. If anybody wants to do that. Okay, where's my exam? Give me 1 second here. No, no. Okay. So this would be, I think this is a good one here. How do we feel about calculating the center of mass of these two objects? Yeah, I'll put this on, this will be on YouTube. I will probably go for like another half hour or so, and then you can find the video. All right, let's just do it then. So the center of mass is like sort of important, but I would not worry about it too terribly much. So we'll just do this really quick and then move on. So remember that in general, like center of mass, right? We could say is this the definition for two objects, just like m1 r1 plus m2 r2 over the sum of the masses, right? Now this is a vector, right? Because it has, at least in this case, it has an x and a y component, right? It's a two-dimensional situation. So for this particular problem, like I tell you essentially what to call things, right? So we'll just knock this out symbolically and then move on. So in this specific example, the smaller object, right, is originally at x equals negative 4.8. So what we would do is we would just, let me just make sure this is a vector. Actually, let's do it component by component, because that's probably what we should do. So this has mass m, right? And it's at position negative L. Now the other mass has x position 0, right? So we just put 0 in here. Now remember, the denominator is just the sum of the masses, so it's little m plus big M. And we find that this is just going to be negative m L over big M plus little m, right? So this is kind of a nice example because these, well, one of them is just on the x-axis and the other is just on the y, right? And so the y position of the center of mass will look similar, but opposite, right? Because now we note that the x position of the the y position of the smaller mass is 0, and the y position of the larger mass is going to be at negative 3 meters, right? So I called that d, so it's negative d over big M plus little m. And then we find, right, that this works out to be negative big M d over big M plus little m. And so I'm just saying that big X is the X component of the center of mass, and big Y is the Y component of the center of mass, right? So what we find, if we want to write this as a vector, is that the center of mass is given by this with its X component, and this with its Y component. Does this make sense? Is everybody clear on this process here? I think the simplest way to do center of mass is just solve for the components separately and then combine your answers in the end. If you wanted to be fancy, you could like factor out the 1 over m plus big M, but that's not necessary. Cool. Okay, so let's look at the second part then. So, right, like this is an example of a collision where two objects collide and stick together after, right? So can we apply conservation of energy here? What do we think? Yeah, we can't, right? No, we can't. So what we would do is we would just write out what, this is how I would do this, right? I would write the initial momentum in the x direction equals the initial momentum, or the final momentum in the x direction, and the initial momentum in the y direction equals the final momentum in the y direction. And so we just fill this in, right? Now, let's see, like, does the bigger object here have non-zero momentum in the x direction? Yeah, no, it doesn't, right? Because it's just moving in the y direction. So we could just put that this is 0 for that. Then after they collide, right now, this is where this gets tricky, or it can get a little bit tricky. But we have to like just sort of make an assumption about what their velocity, their shared velocity, looks like after they collide, right? And I think that like if you think about this intuitively, it kind of makes sense that their velocity vector, their shared velocity vector after the collision, is going to lie in the first quadrant, right? So what we would do, what we could do is we could say something like this. Well, for the right-hand side of my conservation of momentum equation, it's just the combined mass. They will have a shared velocity, right? And the x component of that, we could just say, is given by cosine theta, where theta is the angle their velocity vector makes with the positive x-axis, right? So I'm going to write this one more time. We'll just get rid of the 0 for clarity, but this is basically it. This is basically what we need out of this equation here. Now, for the y direction, it's going to be similar but different, right? Because now the first, or the smaller mass, has no y momentum because it's just moving in the x direction. And the larger mass will have all of its momentum in the y direction, just given by big M v naught, right? Then we do almost the exact same thing. It's just big M plus little m times big V. And in this case, we're talking about the y component of their shared velocity, so it's going to be big V sine theta, right? Where again, theta is the angle that their shared velocity vector after the collision makes with the positive x-axis. And so rewriting this one more time, we'll just get rid of the 0 term, right? Because that doesn't need to be there. And we now have two equations. We wind up with this. Oh, I didn't want to do that. Never mind. But we wind up with this and this. Does anybody see like what the obvious thing to do here might be? Who's got an idea? Yep, exactly, right? We want to just divide one equation by the other. And so if we do that, what we find is we should divide the y equation by the x equation, right? Because we want to get a tangent out of this. So we get this divided by this. And then this is going to equal big M v naught divided by little m v naught, right? And so the nice thing that happens here is like we get rid of this big V that we don't really care about. We will need it, I guess, for the next part, but for the time being, we don't need it, right? And then we get rid of the mass term too on the left-hand side here. Now, as somebody said, sine of theta over cosine theta is just tangent theta. And so to get the angle, we just arctan both sides. Right, theta equals arctan big M v naught over little m u naught. Did anybody get a number for this? If anybody tried it, I think it's like supposed to be 59 degrees or something like that, but I don't remember exactly. I could also just check the email if nobody did. Okay, yeah, that sounds about right. 58 degrees, cool. So how did I get rid of the sum of the masses? Well, look, like I divided this by this, right? So the big M plus little m term cancels, and the big V term cancels, and we're just left with sine of theta over cosine of theta, which of course is tangent theta, and that just makes this nice to solve for with, you know, a numerical result. And you should have found about 58, 59 degrees. Yeah, no, you're good. So that's that. And I mean, like, the thing is, like, you just want to be on the lookout for, you know, when you have two equations and two unknowns, especially, well, I guess this is specifically for cases where they involve, you know, sine and cosine. You just divide the equation that depends on sine by the equation that depends on cosine. And sometimes when you do that, you'll get some really nice cancellations, like in this case. Okay, cool. Does this all make sense? Just an inelastic collision. I guess perfectly inelastic. So just conservation of momentum, no conservation of energy. Yeah, you could do that too. So you could have written, alternatively, you could have written this. You could have written big V sub x down here, and then the same thing, right? Big V sub y, and that's fine because it's two equations and two unknowns, so that works too. Or wait, does that, can you do that? No, I think you would still have to, you still have to divide, right? Because no, I'm insane. You can do that too, because you just solve this for Vy and this for Vx, and you're good to go. Okay, cool. But this is slicker, right? This is nicer, I think, at least. Okay, cool. But yeah, that's a good question. That would be the other way to do it if you didn't think to divide one equation by the other. Okay, so then as far as the kinetic energy that's lost in the collision goes, we just want to write out, right, what it is initially and what it is finally. And this is going to be, yeah, I'll put it on YouTube. So the initial kinetic energy is going to be 1/2 little m u naught squared, right? Plus 1/2 big M v naught squared. The final kinetic energy, I'll email everybody about that. The final kinetic energy is going to be 1/2 big M plus little m, right? Remember, now they're moving as one object. And then it's just big V squared. So what you have to do is you have to go back to one of these equations, right? Now that you have theta, and you have to figure out what big V is, right? So that was the other part to this. Is everybody good with like how you would do that? Does anybody want me to talk about that, about solving for big V? Because the idea is, like, once you've gotten theta, it's not too much work. I'll just do it really quickly here. So if we look at the y equation, the y momentum equation, we would find that big V is given by big M V naught over big M plus little m divided by sine theta. Right? And that would be the V that you plug in down here. And then you would just write delta K is given by K final minus K initial, right? And so it would just be a matter of evaluating this. Now, when I gave this exam over the summer, what lots of students wanted to do was they wanted to... well, okay, so this is maybe phrased a little ambiguously, but the point is that energy is lost in this collision, right? And so, yeah, and so we're not applying conservation of energy here, right? What we're doing is we're just calculating what the change in kinetic energy is. Because if energy had been conserved, this would be 0, right? But if you go through and you plug the numbers in, you find that it's not 0. And so just because you're asked to figure out what the change, or I mean, it's fairly suggestive, right? Because like if no kinetic energy had been lost, then, well, this would just be 0, right? And that would be kind of a silly thing to ask. But the point is that, well, no, it's not really that either, right? Because we don't know what the force is that's causing energy to be lost. It's just like saying, hey, I know that the kinetic energy, like I just happen to know that the kinetic energy after the collision is not the same as it was before. What's the difference, right? So don't try to make it more complicated than it needs to be, because if you tried to use like the expression for work or something like that, you just don't know anything about like the force, right? You would need to know like what force they exert on each other or something, and maybe how long they were in contact with each other for, or something like that, right? So don't overcomplicate it. It's just calculate the kinetic energy originally, calculate it after. What's the difference? Yeah, and the answer should be negative, right? Because you're not going to have a collision, right, where energy is gained. You can have a collision where the energy is conserved, and you can have a collision where energy is lost. But like in a circumstance like this, at least, you're not going to find that the final kinetic energy is larger than the initial kinetic energy. Yeah, and so to find the initial kinetic energy, like what we're kind of asking is like, what is the initial kinetic energy of the system? And so we just look at the kinetic energy that each one has, and then add them together, add them up, right? For the second part, it's a little bit nicer because they are moving together as one object. So it's really just like thinking about the kinetic energy of one object moving at big V with mass big M plus little m. Yeah, okay, cool. How do we feel okay about this? Are there any last questions before we move on to the second problem here? Okay, I'll talk about that really quickly because that would be a good thing to discuss. Well, no, I wrote final. I did. You're right. My bad. Yeah, this is incorrect. Thank you for catching that. So I just put them in the wrong order. This should be something like this rather. Right. Thank you for catching that. So then, so the reason that I introduced the sine and cosine is because like what we're saying, right, is that this is my y-axis, this is my x-axis. Now, we just kind of know intuitively that if these two objects collide like this, they're probably going to wind up moving in the first quadrant, right? And so this then works out to be that there's like a vector that I call big V, right? That, I don't know, maybe it looks like this. And it makes some angle, theta, with the positive x-axis. And so you had a homework problem like this, I believe, where like a lion ran at a gazelle or something. And initially the lion had only like y velocity and the gazelle only had x velocity. It's the same thing, right? You just like assert that after the collision, they're going to have some shared velocity, and it's going to make some angle theta with the positive x-axis, and then you just solve for what that angle is. Or you write their velocity vector in terms of the components, just using like the trig stuff, right? Does this help? Does this clear up the question about sine and cosine? Yeah, cosine is just the x and sine is just the y, exactly. And as we discussed, right, you could have also written it like this. This would be fine too. Actually, this is nice because it actually assumes less than this. Like here we assumed, right, that they wind up in the first quadrant, whereas here we made no assumptions. So that there's actually, I don't know, like this is maybe even a little bit more general, and that has its advantages. But I think we can sort of intuitively just look at this and say they have to sort of be moving between 0 and 90 degrees with respect to the positive x-axis after the collision. Right? So don't forget that, you know, this stuff is all sort of supposed to make intuitive sense based on like what you know about the world, right? That's something that's good to keep in mind. Okay, cool. So then let's look at this one. Let's see here. Okay, so this is like just a lot of, it's like collision, a little bit of work done by friction, right? And then conservation of energy for the last part there. So I meant to specify honestly when I wrote this, what the nature of the collision was. But I believe what I had intended was for them to do conservation of momentum here. So this would be like this would be an example of like sort of a badly written problem in that like it doesn't really give you, I think, a clear sort of indicator of what the nature of the collision is, right? So if you were looking at this and you were like, well, I don't know if I should do conservation of energy or conservation of momentum, that's like probably a pretty natural way to feel, right? I felt bad about it, but I do make mistakes. So, but what we have to do though is we have to figure out, right, what the velocity or the speed of the mass at the end of the string is before it hits the block, right? And this is a little bit subtle. So what we have to do, I'll have to make a picture for this, and it's going to be awful, but it should get the point across. Is we have to note that the length of this chord is constant, right? It's more or less going to stay the same. I'll actually use the straight lines here to make this better. So imagine that the sphere is at the end of this line that I've drawn, right? This is like what the chord looks like right before the sphere hits the block. And this is what it looks like initially. Okay. Now we know that, like I was just saying, that the length here is L and the length here is L. We also know that this is theta. Right? So we just have to do a little bit of slick trig to figure out what the change of height, or what the height of this thing is initially above our equilibrium position, which I'm defining my y equals 0 to be basically the center of mass of the sphere when the string is vertical, right? In case that wasn't clear. And so I would do this, right? I would just say, okay, let's make this into a right triangle, but it's not exactly a right triangle because this is L and this is also L. So what we do is we note that this could be like, I don't know, let's call it H. This height basically that the string, the end of the string has originally above where it finally winds up. And then this here, right? So once we realize that, we can write that the height of what's actually the right triangle here, which is kind of not including this part, is just going to be L minus H. And so now we can do like cosine is what I think we want to do here, right? Is the sketch clear for everybody, first of all? Because when we take cosine of theta, we just do adjacent over hypotenuse, right? Okay, here. And so this is going to be script L minus H over L, right? And so from this we see that L minus H equals L cosine theta, right? And then we just have to solve explicitly for I forgot the G, for H, which ends up giving us, right, we just add H to both sides, subtract L cosine theta from both sides, we find that this is L minus L cosine theta. So then we can apply conservation of energy to figure out what kinetic energy this thing has, or I should not kinetic energy, sorry, what momentum this thing has right before the collision, because we want to apply conservation of momentum, right? So what we do is this. We say mgh, right? Remember, little m is the mass of the sphere, equals 1/2 m, and we'll just call it v naught. V naught is the velocity that the sphere has right before it hits the block. Could you solve for the velocity right before the collision using Newton's second law in circular motion? That seems like something you might be able to do, but I don't think so. I don't think you have enough information. And I mean, this was, and that, I mean, that's a really good question, because like the stuff that we've been covering involves both energy and circular motion, right? So what I think you would find is if you tried to do that, you would just realize you don't have enough information, hopefully, and you would just have to try like a different approach, right? Now we want to just plug in like what what H is explicitly, right? So it would be like this, mg L minus L cosine theta equals 1/2 m v naught squared. Yeah, like when I'll get a numerical answer and you can tell me if it's the same that you got. I'd be curious to know. I just wouldn't have thought to do it that way. And we can like clean this up, right? We cancel the masses. That's a nice thing. We can actually like even factor out the L here. So this just becomes 1 minus cosine theta. And I'm just doing the math here. We multiply both sides by 2, right? And then we find that that V naught, V naught equals the square root of 2g L times 1 minus cosine theta, right? So this is the velocity that this sphere has right before it hits the block. And this is actually, like, if you think about how this is sort of set up, this is actually its x velocity, right? Because basically because the string that it's attached to is perfectly vertical when they collide, okay? So we have this now. Then we apply conservation of momentum to the actual collision, right? So conservation of energy was just something we needed to actually be able to do conservation of momentum for the collision. And this then looks like, remember, we're talking about the x direction here. So we could write P initial x equals P final x, and we would write m v naught equals, and then, so in the problem statement, right, I said that the sphere comes to a dead stop after the collision, so there's only one term on each side of this equation, right? Obviously, there in general can be more, right? There could be, you know, it wouldn't be surprising if there are two terms for a collision involving two objects, but just because of the way the problem is stated, right? And let's just say that this is equal to big M, and I'll write big V naught, right? So then just plug in what V naught is. It's all this crap. And then this equals big M, big V naught. And finally, right, we just divide both sides by big M, and we find that big V naught is this. So you could actually, like, if you just plug the number, well, let's just get the numbers right now because I'm curious also about this. But so for those of you who did it with like circular motion and stuff, just tell me if this is what you ended up getting. But let me just do this. 2 times 9.81, 4.4. Okay. And then 0.3 times 1 minus cosine 30 degrees. And then we divide that by 1. 2 times L, 1 minus cosine theta. Yeah, okay, cool. 4.44, is that what people found when they did it with circular motion stuff? Okay, so then yeah, so then it would seem that probably using circular motion was not going to work here, unfortunately. Okay. So then now, right, the block is going to just move. It's gonna start sliding along the ground, and it's gonna hit like the patch of floor where there's friction. And so the sort of the quick and dirty way to do this here is let me do it like the standard way, I guess, first though. We're just gonna say that, right, conservation of energy. We could write this delta E. No, we want work energy theorem, my bad. It's the easier thing to do here. So remember that change in kinetic energy, right, is just going to be 1/2 m, and I'll write big V squared for the final velocity, right, of the block after it exits the patch of floor where there's friction, minus the initial kinetic energy, right? This is the kinetic energy it had like right when it got onto the part with friction. And so then, yeah, you know, so I meant to say, right, I meant to say in the problem statement that, like, I meant to give them some sort of indication that they should use momentum and not conservation of energy. But, like, lots of students did do conservation of energy, so it's my bad, right, as I was saying. And I gave them, like, pretty generous partial credit. But it also kind of comes down to, like, what I was saying before is that conservation of momentum for collisions will work more often for you than conservation of energy will. Right? So I definitely said that to my students, but like apparently I didn't stress it enough. But like I said, I meant to put something in the problem statement to indicate which they should have, like which approach they should have done. Conservation of momentum versus conservation of energy. Okay. So this is the first part of the work energy theorem, right? There's only one force that's doing work here, right? And it is the friction force. And so what we would do is we could just write something like this. We could write negative Fk times L, right? Because it's a force times the displacement. And it's negative because if you were to draw the free body diagram here, the friction force would point to the left, right? But the block's displacement is obviously to the right. And so that means cosine of theta, cosine of 180 degrees, -1. So it's negative work. And also it just sort of matches up with our intuition that friction is a dissipative force, and so it should be doing negative work. Now we just have to plug this in, right? We just have to remember that the friction force is the coefficient times the normal force, right? And then in this case, the normal force is just mg. But remember that the normal force isn't always going to be mg. Like if it were on a ramp or something like that, right, you'd have to just maybe make a quick sketch or make a quick free body diagram to figure out what the normal force would look like in that case, because it won't just be mg. We can just jump to this because it's on a horizontal surface. But this is what we have, and you know, again, we can go through. We'll clean this up a little bit. We'll just multiply both sides by 2, and cancel the masses while we're at it. And so this is what we get. And then we finally find, right after we just do a little bit more algebra, that the block's speed after it exits the frictional part of the surface is just going to be v naught. Sorry, let me do this. Square root v naught squared up to the first minus 2 mu sub k g l, right? Like this. And this suggests that its velocity is lower, which makes sense, right? And you know, notice actually that this very much looks like one of our kinematics equations, which was something like this, right? This has the exact form, except what this is saying is that, right, that like this acceleration is to the left. That's why there's a negative sign here. And the velocity, the x velocity, is to the right initially. So when you apply the work energy theorem, you should just kind of, as a sanity check, like try to make sure that you come up with something, especially if you're solving for like the final velocity, that resembles a kinematics equation, right? In particular, this kinematics equation, because this is exactly where the work energy theorem comes from. Well, I don't know if I could say that, but like you can at least convince yourself that the work energy theorem makes intuitive sense starting with this equation. So then we could just figure out what this is really quickly, I guess. Or you know what? I don't think there's a point. Do people want me to get the number? Do we care? I'm just going to get it. That looks good. So it doesn't actually change by a whole lot, right? But I'm pretty sure this is correct. It should be like 4.117 meters per second. Yeah, I can talk about that in just a second. Let me just kind of take this to completion, and then we can talk about like we can talk about that in a little more detail, because it's not so bad from here, right? Because at this point it's just bare conservation of energy, because as soon as the block leaves the frictional part of the surface, there is no work being done by non-conservative forces, right? It's my laundry, okay. How soon after this is over will the VOD be available to view? I mean, I'll get it uploaded as soon as I can. I don't really know. It probably takes like 30-45 minutes to process, and then it'll be there. Let me just knock this out really quickly. So we have to do this thing, right, where we solve for the height of the triangle. Oh no, wait. Yeah, we do have to do this, right? Because the final height h is found via this, right? It's found from saying sine of theta equals h over d, right? Because and we have to use the height because we want to do we want to use the gravitational potential energy as part of our conservation of energy equation, right? So this just tells us that h equals d sine theta. Like this was something that you also had to do on the first exam, something like this, right? So it's probably pretty familiar. So then we just set E initial equal to E final. E initial is 1/2 big M, big V squared, right? Where big V is what we found here. Here. And then this equals big M G H, right? But H is D sine theta. So we can cancel the M's. And then we solve for D, right? So somebody check me in here because like I cannot do algebra for the life of me, but I think it's going to work out to be big V squared over 2 G sine theta. That looks good, right? Whatever this number works out to be should be your answer. But this is, just to stress this is conservation of energy with, like, you know, no modifications, because there are no non-conservative forces that are doing work here, right? So I'll talk really quickly about that, the question that somebody had about the normal force, because this is like definitely good to see. So the question was like, what does the normal force look like if you have an object that is on a ramp? And like this is sort of just an exercise in Newton's laws, right? So say like this is my ramp. We know that it makes some angle theta with the horizontal. And my object is like, I don't know, it's like here. So we put the forces in, and if we're just going basically off what's going on in like this particular problem, there's no friction, right? So the only two forces are the gravitational force pointing straight down and the normal force, which remember is perpendicular to the surface. So quick trig, right? Like the angle that the gravitational force makes with this line, this dotted line that I'm drawing, is also theta, right? This angle is theta. And so for this kind of a situation, if you just sum the forces in the y direction, spelling is hard, you find n minus mg cosine theta equals 0, right? So then n is mg cosine theta. And you could actually just, you know, you could say basically that the normal force is always this on an object that's on an inclined plane at an angle theta above the horizontal, because even if there's friction, right, the friction force is going to have no component along the surface of the ramp, right? And so it doesn't appear in our y net force equation. So this is what that would look like. So if this had been on a slant or something, then I would just have written mg cosine theta here instead of just mg. Okay, cool. Let's see, what else is there? Can you do the third part of problem 3 on the other exam 2 study guide? Let me see what that is. Probably will like, this will probably be the last thing that I do. And then if you have any questions or whatever, just hit me up. Maybe I could even try to get to the exam a little early if people want to ask before. Problem 3 here. Geez, okay. So this, so I think what I'll do is, wait, so you wanna look at this one? How do you feel about problem 3? Because I think that would be more instructive personally. And I'm confident I can do this one pretty quick because I have looked at it before. All right, let's knock this one out. And this will be kind of fast, but we can hopefully get it done. I also like this one because you get like a really nice result at the end. Okay, so magnitude of the normal force acting on the block when it is at the lowest point of the track, right? So he says the track is still circular here, right? Which kind of maybe indicates that we want to think about circular motion. So we just look at the net force in the y direction, right? And if we made the free body diagram, we would just have the normal force pointing up and the gravitational force pointing down, right? But we would have to remember to set this equal to m times v squared over r, because as we just said, it's still in circular motion, right? So we can't quite take this to completion yet because we need v, but we get that from conservation of energy, right? So if we write this, we initially have just gravitational potential energy because it starts at rest, right? And this is converted into kinetic energy. And so this tells us, right, that v squared, I'm not even going to solve for v here because I know that we need v squared for our net force equation anyway, right? That v squared, we can cancel, let me just do this. For me, cancel the m. Yeah, and we find v squared is just 2g big R, right? So then we take that up here, and we can write that big N minus mg equals m times 2g r over r, right? So big N equals mg plus 2mg, right? So it's just 3mg. And so this was obtained, right, from a combination of the circular motion stuff and conservation of energy. Cool. Okay, let's look at part B. How much work, including sign, does the friction force do in the block as it is brought to rest along the incline? So what we can do here is we can write that, let's say conservation of energy again, right? E1 equals 1/2 mv squared, where v is just what we just found, right? It's just 2g big R. And then we could say that E2 is just going to be gravitational potential energy because it comes to a stop, right? He says in the problem statement it's brought to rest. So it makes it to a vertical height of r over 2. Okay, yeah. So this is just r over 2. Now, if you were to like compute this numerically and then compute this numerically, you would find that these values aren't equal, right? And that's one sort of indicator that we need to think about the work done by the non-conservative force here. So we could write delta E, which is of course E2 minus E1, equals the work done by the friction force. Now, E2 we don't have to like do anything with. It's pretty much already in the form that we want. But now we have to go back and we have to substitute in for v squared again. Because the initial energy was just kinetic, and again I'm just defining y equals 0 to be basically at the ground here. So from here, right, we found v squared is just 2gr, 2g big R. This equals the work done by friction. This becomes 1/2 mg big R, minus mg big R, which equals the work done by friction. And we could already see, right, that this is negative because this is going to work out to be the work done by friction is negative 1/2 mg/. And this is necessarily negative. So how did I replace h with r over 2? Oh, because he says, right, that wasn't immediately clear to me either, but he says it makes it to a vertical height of 1/2 r equals 20 centimeters. So it's just in the problem statement. So we find the work done by friction. It's negative as we would expect, right, for a dissipative force like friction. So the last thing to do here is, I believe we want to apply the work energy theorem at this point. Yeah, so let me just do like the trig. We have, and if you don't see why I'm doing this, you'll see in a second, but we have that sine theta equals the height of the incline, which is r over 2, divided by L, right, where L is the hypotenuse of the right triangle that makes the incline. And so this tells us that L equals r over 2 sine theta, right? Now, work energy theorem, its final kinetic energy is 0 because it comes to a stop, right? So we could just say 1/2 mv squared minus 0 equals negative mu sub k. And then this is going to be, this is an example of where we actually have to use what we were just talking about, right, with the normal force for an object that's on an incline. So it should be mg cosine theta, right? This is just the normal force. And then let me write this explicitly. I don't want to lose anybody. So this is what I'm saying, right? So then this becomes negative mu sub k. The normal force is mg cosine theta, and L should be big R over 2 sine theta, right? I'm doing, I'm algebra in my head and stuff. I'm not going to guarantee I'm not making any mistakes, but like the procedure here is definitely correct, if nothing else. So we can make this nice. We can get rid of the masses, right? Because there's an m term on both sides, and we just have v squared over 2 equals negative mu sub k g r over, and I'm going to take cosine of theta over sine theta and turn it into 1 over tangent theta. And I have to remember to put a 2 here. Is that equation the work non-conservative equals delta? Well, it's the kinetic energy, right? Not the mechanical energy. Kinetic energy is something that contributes to mechanical energy, but like when you're using the work energy theorem, you want to use just the kinetic energy. So we get v squared equals this. But v squared, right? V squared is just 2g over, or 2g times big R, right? From what we had before. So we could do this 2g big R. So we can cancel these 2's. We can cancel, actually we can cancel gr, which is cool. So now it's just 1. Oh, but this is, wait, something is not right here because, I did it again. I did initial minus final, not final minus initial. My bad. So let me fix this really quickly. This should be 0 minus 1/2 mv squared. I apologize for that. Easy enough to fix though. And then this is actually going to turn into -1, right? Because we just now have a negative sign on both sides, which we'll get rid of anyway. So we end up finding, right, that mu sub k should just be 2 tangent theta, if I didn't make any other mistakes. But it is just going to depend on the angle, right? The tangent of the angle. I'll calculate it really quickly just to see if that's what we actually are supposed to get, because the answers are, oops, see, this is why OBS is annoying. Let's see here. So 2 times tangent of 30 degrees. Okay, thank you, that's helpful. What? No, I don't think that's right. We should have found, I think we should have found that it's just tangent. What's going on here? This. I made a mistake for sure. It's probably just a stupid little algebra thing. Yeah. Okay. So what I think I want to do actually is like probably what Nero intended, and I'll fix this, is I want to write that the work, I just want to use like the definition of work, right? As it being the force times the, or the dot product essentially of the stuff. So what I should have done, right, is just written that -1/2 m. I'm not get ahead of myself. The work done by friction is negative mu sub k big N times L. Now I'll get rid of all this. This won't take very long. Okay, so -1/2 mg big R equals negative mu sub k. Normal force was energy cosine theta, and then L was big R over 2 sine theta. Okay, so I cancel the masses, right? I turn cosine of theta over sine of theta into 1 over tangent theta, and I cancel g also, and I cancel the 2's, right? So I'll just copy and paste this, do it term by term. So we get rid of the 1/2, we get rid of the 2, we get rid of mg, actually we get rid of r as well. And we get rid of the negative sign, because just multiply both sides by -1, same thing. Okay, so we find that 1 equals mu sub k over tangent theta. And therefore, right, mu sub k equals tangent theta. And then if we do this, right, this was, so we just divide this by 2, or I'll just do it again. Tangent of 30 is what we should have. And it's what we're supposed to get. It's 0.577. The work. Why does the work done by friction equal the frictional force? Well, it's not that the work done by friction equals the frictional force. Remember that we're taking the force and we're multiplying it by the displacement, right? So that's gonna be a big thing to look out for, like tomorrow, right? Because if you had forgotten to write L here, you would be saying that the work done by friction is just the friction force, and that's like, it's kind of a big mistake, right? Because work and force are not the same thing, right? So just make sure you're taking your time, and like whenever you write down explicitly what the work is that's being done by a force, make sure you have like a force times a length when it comes down to it. So work done by friction is equal to friction force times distance times cosine theta. Yeah, and the friction force is nice in this. This is probably like the last thing I say before we finish here. But the friction force is nice in this case because I can just use the diagram I had from before. Now, the friction force will point like this if I could draw a straight line, right? And the displacement of this thing, the displacement vector, is like just like this along the surface of the ramp, right? And so we see that this would be like my d vector, you could say. So there's an angle, first of all, of 180 degrees between these things, right? Which is why this is negative. Cosine of 180 degrees is -1. And then we just have to remember to multiply it by the magnitude of the displacement, which is L, right? Which we had to solve for. It's not, you know, it's not as nice as just writing L, but it's not so bad once you just do the trig. So just make sure that whenever you're calculating work, right, whenever you write an equation for the work is this, if you're writing it out explicitly, it should be a force times a displacement, because work and force are just very different things, right? Does that make sense? Cool. Okay, I'm gonna, just because like I have to, you know, upload this still and email everybody and all that. I'm gonna end here. If you need anything between now and the exam tomorrow, just hit me up. You know, I'll try to get you straightened out, and I'll see you all tomorrow. Give me 1 second here. If I don't have your, like, are you like in Mark's class or Dr. Nero's? Because I can just give you my email. Yeah, cool. I just whispered you my email, so you can just hit me up and then I can send it. Okay, but like seriously, next time, like I'm gonna have to like make some of you mods, so